Hello everyone, my name is Pramudita Pereira. In this video, I will be introducing some concepts related to deep learning by taking a signal processing application as a running example. So if you are familiar with signal processing, I'm also making some connections between deep learning concepts and signal processing. If you don't have a background in signal processing, that is also fine. You can simply skip those sections and continue with the video. In order to introduce concepts in deep learning, I will use this running example. My example is a 1D signal, a EEG signal, and the objective that I'm trying to achieve is to determine, given a EEG signal, whether a heartbeat exists in the given signal. So what you see in the screen is an example of a EEG signal where heartbeat exists. So this portion over here is a single occurrence of a heartbeat, right? So given a signal, how do you do this? So I will use this example as an intuitive example to introduce concepts of deep learning. Okay, so before we move there, let's remind ourselves how signals are represented in computers. So outside, the real EEG signal is going to be an analog signal. Given an analog signal, first we go through a sampling process and then we go through quantization to convert these analog signal into a discrete signal. So these discrete signals are represented with numbers. For an example, if we consider 8-bit quantization, what it means is that we will represent the signal intensity of the signal with numbers from 0 to 256. So what will happen is in cases where the signal intensity is very low, for an example, cases like this, we will assign number 0. For cases where the signal intensity is very high, situations like these, the peaks, we assign number 256. So in between, depending on the intensity of the signal, we will assign a number. So at the end of the day, inside a computer, what we have as the representation of this analog signal is a stream of numbers. For an example, in this case, maybe the stream will start around 128. Then there's a small jump here. So maybe it goes to 130. Then it goes down to the base value, 128. And then a series of 128 numbers. And then there's a jump relatively higher. Maybe it goes to 150. Okay. So this signal is now represented by a stream of integer values. So this is what we observe inside the computer. Now, the problem is given a stream of integers that represent an outside signal, how do we determine whether the original signal consists a heartbeat? For the remainder of the video, I will call this signal as the input signal and I will denote it with symbol X. Now, what is the intuitive way to solve this problem? One approach would be to define a template that describes the signal that we are looking for, the signal of a heartbeat, and check whether the original signal has some resemblance to this template in any of their location. For an example, let's define our template to be this signal. So my input is X, my template is T. So remember, my input is a stream of numbers, so is my template. So let's say my input has a size of n and my template has a size of simple t. So what I will be doing here is I will be looking at the correlation between my template and my input signal. So what I will do is first I will consider the first t points in the input signal. So what I will be doing is I will be taking the correlation between this template and the first t indexes of this signal, right? In other words, I will be checking whether the first t indices, in other words, this window of the signal, does it look similar to my template? So in this case, we can see it's not exactly similar. There is some overlap, but it's not exactly similar. So when I take the correlation between these two values, the correlation will not be very high. So mathematically, what I'll be doing is I'll be taking the dot product between my template and the first t indices of my signal. So this value is not very large. For example, let's say this will be around 10. And then what I will do is I will move this window by some indexes and then calculate the correlation between the template and the new portion of the signal. So for an example, now I can look at this second window. Again, there is some overlap between these two, but when you take the correlation, when you multiply index by index, since these two signals are not exactly aligned, the correlation will not be very high. Okay, so let's say when I take the correlation again, I'm taking the correlation between the template from T to 2T, right? Maybe here again, our correlation number is around 12. So I can continue to do this. So when I move further forward to the third location, now the signal is exact match, right? So in this case, my correlation will be very, very high, right? So for an example, 2T to 3T, maybe this will be very high, something like 50. At the same time, if you consider a window where there is no signal present, right? The signal is completely flat. Then the correlation between that portion of the signal and the template will be zero. So as we continue to slide my template over the original signal and get the correlation between portions of the signal and the template, we continue to get numbers that basically indicates whether the signal is present in a particular window of the original signal. So when we do a complete sweep, what we will get is another stream of numbers. So in this case, it will be 10, 12, 50, so and so forth. This second stream of numbers that we get as the result of this operation, we call these numbers a feature. So these numbers describe whether the template that we used was present in a signal or not. So that information contains in this new vector that we call as a feature vector. So when we talk about the dimension of the feature vector, the dimension of the feature vector depends on the original dimension of the original signal, the dimension of the template, and also the overlap between my windows. In this case, I considered there is no overlap between two consecutive windows. So in that case, the dimension of the feature will be n divided by t. So this kind of a approach will give me a second feature signal which will contain some information whether the original signal had similar components to that we are looking in the template signal. So once we have this feature, let's call it simple f, we can use that feature to determine whether there was a heartbeat in the original signal. So how do we do that? From our discussion, it's clear that when the original signal contains a similar profile to that of the template, one of these values should be very large. In situations where there is no common similarity between the template and the original signal, all these values should be very low. So we can use that logic to determine whether a heartbeat was present in the original signal or not. We can simply take maybe the average of the feature. If heart rate was present, at least one of the components needs to be very high. We can look at the average and introduce a threshold. So what we can do is we can check if the average of this feature signal is above some predetermined threshold. If the average is above a predetermined threshold, we can say that there is a heart rate present in the original signal. Otherwise, we will say there is no heart rate present in the signal. So a relationship like this is known as a decision rule. Now, let me draw some parallels between this intuitive solution that we came up with for heart rate detection with signal processing. So if you remember, in order to get this feature vector, we looked at the correlation between the template and portions of the original signal, and we basically slided the template over the signal to get the correlation value at different indices. So for anyone who is familiar with signal processing, this process looks very similar to convolution operation. So this is exactly how do we do convolution in signal processing. Because of this, we can say that my output F is in fact a convolution between the signal X and the template T. So what's happening here is effectively we are convolving the signal X with a filter T, right? So output F is going to be a convolution between a signal X and a convolution filter T. Therefore, this template is also known as a filter. In signal processing, we call it a matched filter. Now, let's take a step back and try to summarize this process with a different structure. So we started with the input signal. The input signal had a dimension of n. Practically, we were talking about n values as the input. And then we convolve this input signal with a filter. So the filter size was T. So what we had as a result was a feature vector. So the size of the feature vector was n divided by input is size n, convolution filter size is T, the resulting feature vector is n divided by, and then we subjected this to a average operation. The average operation can be thought about as multiplying every number we have in the feature vector by a weight of 1 over this quantity. So let me denote that as a multiplication and a addition. So in this case, I'm multiplying every number with the same value. Let's call that value W for now. Each number is W, and we are basically taking the summation over this number. So this is my final value. And my decision rule is basically checking whether this value, the final value, is greater than a certain threshold or not. Here, let me remind you that W in this case is going to be the reciprocal of number of components we have at this vector location, which is going to be T over capital N. This is another way of representing what we just did. So this is a commonly used notation in neural networks and deep learning. Now, in deep learning terminology, we call this first input signal as an input layer. So in our application, we took the input and passed it through a convolution filter. In deep learning, we term this convolution filter as a convolution layer. And finally, the output of the convolution layer, which is the feature vector, we did some weighted summing to get the average number, which was the output of the process. So this kind of an operation where we linearly weight each component and add them together is known as a linear operation. So in deep learning, we would call this operation as a linear layer operation. So we have an input layer, convolution layer, linear layer, and at the end, we have the output, which is the output layer. So in fact, the solution we constructed by going through our intuition can be represented as a neural network. So what you have here, in fact, is a simple neural network. But remember, in this case, all the parameters that were used in our construction. So what were the parameters? The weights of the convolution layer, we obtain it through a template of a heartbeat signal. And then the weights of the linear layer, these parameters, we set it manually to be equal to this number by considering the number of features. So all the parameters in this network was in fact selected by ourselves. So there is no machine learning involved. In machine learning, the difference is we will use data to manually learn all these parameters. So in the case where parameters are set manually by experts are called expert systems. In cases where the parameters are learned through data, we call them as machine learning systems. Right. So before we dive deep into machine learning systems, let's talk about what are the limitations of the solution we construct. The first limitation is the output is sensitive to signal intensity. When we take the correlation between my template and the input signal, in order to get a high correlation, the intensity values need to exactly match. But we know in practice, there are certain situations that cause the signal intensity to go up or to go down. So in a situation where the signal intensity is slightly lower, the correlation value will not be very high and we will not detect a heart rate signal. So to solve this problem, the simplest thing we can do is to always normalize the signal before we feed it into the system. So for an example, when before we feed the input signal into the network, we can perform a normalization. So how do we perform normalization? There are many ways that we can do this, but the simplest thing is to do z-score normalization. So what is z-score normalization? We basically, given a signal x, we define the normalized signal by deducting the mean and by dividing the resultant signal by the standard deviation. So if we do z-score normalization, the issue of variable intensity will not be a problem anymore. Now, the second problem that I can identify in the current system is that, like we are matching any input with a single template. But as we know, the heart rate signal can also vary from person to person, depending on their age, their genetic structure, like due to many factors. The heart rate signal of every individual may not look the same. So in that case, when in situations where heart rate of a person is different from the typical heart rate template we have chosen, the system will fail, right? So in order to solve this problem, what we can do is rather than relying on a single template, we can define multiple templates. So let's say we define multiple templates, right? So this template will have a slightly different shape. This template will have a slightly different shape, right? They both are still templates that contain information about heart signals, but they are going to be slightly different to each other. Earlier, our system had a single filter. Now we have multiple filters. So in this situation, we call that we have a filter bank. Now, how is it going to change our existing system? Remember earlier when we do a convolution between a filter and a signal, we got a feature vector. Now similarly, when we have multiple filters, what will happen is that we will get multiple feature vectors. Earlier we only had a single feature vector. Now we will get multiple feature vectors. So how do we deal with this situation? So each feature vector will have the dimension of n divided by t. Now there are multiple feature vectors that tells whether the given input signal contains one of the heart signals that we are looking for. The simplest thing we can do is to look at all these intermediate feature signals and take element-wise average or element-wise maximum to construct a new signal. So for an example, let's say my feature 0 had values 5, 10, and 20. Feature 1 had values 6, 2, 3. Feature 2 had values 0, 10, and 15. So what we would do is we would take element-wise maximum considering all my feature vectors. So here when I consider these three numbers, maximum is 6. When I consider these three numbers, maximum is 10. When I consider these numbers, maximum is 20. So by doing this, what we have effectively done is reduce a set of feature vectors into a single feature vector. So these kind of operations in deep learning are known as pooling operations. So when we take the maximum, we call it max pooling. When we take the average along a dimension, we call it average pooling. Now let's go back to our network. So earlier we had a single convolution filter which resulted in a single feature vector. Now the things are going to be slightly different. So what are the differences? Instead of having a single convolution filter, now we are having a filter bank. We still call this collection of filters, this filter bank, as a convolution layer. Now, the only difference is earlier we only had a single convolution filter of size t, but now we have multiple of them. So in this case, I'll just say there are three filters. Now what will happen is we will get multiple features as the output of the convolution filter stage. So what we did was we used pooling operation to reduce this entire feature space, entire set of feature vectors into a single feature. So once we do this, our network is same as before. Again, we can pass an input signal, get convolution outputs at each convolution filter to get multiple features, pool these features to get a single feature, and then we have a linear layer here which will do weighted summation over activations to get the final output. So that is the output layer. So we just make our network a little more sophisticated to support better functionality. Okay, so with the setup we have so far, what do we have, right? We have this neural network, a simple neural network, which will take an input signal, pass it through some convolution layer, get the output, the feature vector, pass it through the linear layer, and get the output value at the output layer. Okay, so by design, the output value here will be high when the input signal contains a heart rate signal. That value be low when it does not contain a heart rate signal. Okay, so I wanted to go through this example to introduce you to the basic components of deep learning and to show how they relate to an intuitive solution that we might come for a specific problem. Okay, so this kind of a system where everything was designed by expert is known as a expert system. Now, what is the difference between an expert system and a machine learning system? In a machine learning system, rather than deciding all these values by the expert himself, these values will be initialized randomly and we learn these values using data. Okay, so how that will happen is first we will collect lot of data that contains heart rate signals and that does not contain heart rate signal. So this data will contain some positive signals that contains heart rate signals and negative signals that does not contain heart rate signals. So one important component here is that we need to know what is in data exactly, right? In other words, we need to know, given a data sample, whether it really contains a heart rate signal or not, right? We call this as the label of the data, right? So my data now is going to be a tuple. It's going to contain the actual signal and a label. Maybe this label will be 0 when there is no heart rate signal. Maybe it will be 1 when there is a heart rate signal. So this collection is called as a data set, and typically we need a lot of data, right? So this should be maybe 1,000 to maybe something like 1 million even nowadays. So once we have data like this, what we will do in machine learning is we will initialize all the parameters in our system by random values. All the parameters in my system. So what are the parameters? The weights of my convolutional filter bank, and also the weights in my linear layer. All these parameters will now be initialized randomly. So when things are randomly initialized, this network is not capable of doing anything intelligent. If we insert a signal with heart rate, the output will be either low or high, right? Because the system doesn't contain any meaningful information when we initialize it with random numbers. But our objective here is to learn the parameters, learn all the parameters in the system in such a way that when we input a signal with heart rate, the output will be high, otherwise the output will be low. So how do we do this? So first of all, in deep learning, we work with probabilities. So rather than having a integer value or float value output, what we want to have is a probability output. In other words, we want the output to be between 0 and 1. So one common way to convert a output value, a score value, into a probability value is to use the function which is called the sigmoid function. So here you can see the shape of the sigmoid function. For any value from negative infinity to minus infinity, the value of the function is constrained to be between 0 and 1. So regardless of what you pass here, the value will be between 0 and 1. So what typically happens is we use this function sigmoid. If the output of this network is S, we pass this function S through the sigmoid function to get a probability value between 0 and 1. When we know what is the correct label belonging to a particular input, using the network, we can get the probability of the out. So in this case, if my label says that the given data point is a positive sample, a sample with a heart rate, the probability in this case will be given by sigmoid S. Remember, S is the score value we get at the output of the network. And when the label says that the signal does not contain a heart rate signal in the input, then the probability of not having a heart rate is going to be 1 minus sigma S. Why is this is the case? Because the probability of having a heart rate and not having a heart rate should equal to 1. The summation should be equal to 1. So we can say not having a heart rate, the probability value is 1 minus sigma S. With this formulation, given an input and a label, we have a system to get the probability of that label. So as we learn the network, our objective is to find optimal values for parameters in this network, weights of that network, such that the probability of the given label is maximized for all data. So we can express this as a mathematical optimization problem. So what we are looking at is the probability of a given label given data and parameters. I want to maximize this, and what I am changing, I am changing the parameter, right? So this is a optimization problem that we can solve. This optimization problem is in fact similar to maximizing the log probability, because log is a non-decreasing function. Therefore, rather than maximizing probability of this quantity, we can maximize the log probability. But this statement is also equivalent to minimizing minus log probability. So in deep learning, usually we don't list this as a maximization problem. Instead, we list this optimization as a minimization problem. So how do we solve this optimization problem? Stochastic gradient descent algorithm, and some of the variants. So in practice, we use an algorithm called backpropagation to do this operation. So what do? We initialize all the network parameters with random variables. We have a data set which contains input samples and labels. We pass input samples through the networks, get the final score. Based on the final score, we can get a probability score. So once we get the probability score, we can use gradient descent algorithm to change the parameters of this network such that for most of the data we have in the data set, the output value, output probability of a particular label matches the ground truth label. So that is how we perform the network optimization, and that's how we learn the network. So this quantity that we are trying to optimize, we call this the loss function. So initially, when we look at the loss function, initially the loss is very high when we start training the network. But as we do training, right, as we change the parameters depending on the loss function, the loss goes down. And after lots of training, the loss stops changing. So here we say that the loss converged, right? So when this happens, we can stop training. Once the network is well trained, we can anticipate it to behave the way we wanted it to behave. In other words, depending on how we labeled our training data, we can expect this network to predict labels for the input samples that we provide, right? So in our applications, if we do the data set labeling correctly, we can expect the network to identify a sample with a heart rate as a positive sample and a sample without a heart rate as a negative sample.